Right? This diagram on slide 14 is a very useful diagram. The numbers that are shown here, I would say, are great for review because they show us a lot of our normal values that, that we would be interested in. For instance, we have the atmospheric pressure breakdown. We just looked at the way that we would calculate the individual partial pressures, the pressure that each one of these gases exerts in a mixture of gases. 600 millimeters of mercury for nitrogen. For oxygen, I usually round this up to 160 rather than 159. And then for the partial pressure of CO2, you'll notice that one looked different than what we saw before when we calculated it directly using Dalton's law. We got 0.23. Here we're really rounding it up to 0.3, right? There's going to be some variation there in terms of the percentage of CO2 in the atmosphere. And this is just an easy number to use, 0.3. What we see happening then is that when we compare these individual partial pressures for each one of these gases to the individual partial pressures that are found within the alveolar space for each one of these gases, we see that there is a partial pressure gradient, right? When you go to exhale, you don't remove all of the air in your alveolar spaces, right? You have a residual volume there, and that residual volume is shown here. So you get the mixing of gases upon inhalation with the proportions that are in the alveolar airspace. And that means that the partial pressure of nitrogen decreases. That will decrease. Partial pressure of O2, that also decreases. But the partial pressure of CO2, that increases. Right? You have that spent air that's left there, residual volume. You inhale, you get the mixing of those gases, and that's going to change those partial pressures. So these partial pressures are now what is reflected, right, in terms of that mixing that has occurred. What this means now is that we have a pressure gradient from outside the body into the alveolar space. We have that for nitrogen. Nitrogen is higher outside than inside. Nitrogen will flow in. Okay. Oxygen, 160 outside. Partial pressure of oxygen inside your alveolar spaces, 100. So oxygen will want to flow in. But the partial pressure of CO2 within that residual airspace, that residual volume, is higher than it is in the atmosphere, which means according to our partial pressure gradients, that CO2 is going to diffuse out. Right? Then we have to make another comparison for our partial pressures, that between the partial pressures in this residual airspace within the alveoli and the capillaries, the pulmonary capillaries. Here we have deoxygenated blood coming to the pulmonary capillaries, then oxygenated blood leaving the pulmonary capillaries. And we're shown here that the partial pressure of oxygen that we would measure in venous blood coming to the lung capillaries is around 40 millimeters of mercury. So we've had oxygen dropped off to the tissues, and the proportion of oxygen that remains gives us this partial pressure of oxygen, 40 millimeters of mercury. And then we compare that to the partial pressure in the alveolar space, and the partial pressure is higher in the alveolar space, which means that the oxygen is going to want to diffuse into the blood, down that partial pressure gradient. and that oxygen will continue to diffuse during the transit time that's described later on, continue to diffuse in that short transit time until we reach equilibrium, and now the partial pressure of oxygen, and now the oxygenated blood that's going to leave the capillaries should be around 100 millimeters of mercury. There's our partial pressure. And at this point, if we have normal perfusion ventilation matching, then we should see that we have 100% saturation of our hemoglobin when we reach this 100 millimeters of mercury for partial pressure. But keep in mind, this measurement itself would be what we're measuring in terms of the partial pressure in the plasma. Right? It doesn't tell us anything about what the hemoglobin is holding. To get that information, we actually have to measure hemoglobin concentration, right? And assume that we have full saturation of that hemoglobin, something that we'll talk about later. But what this represents is the pressure in the plasma. There we go. Same is true of the other gases here. Now, if we look at the partial pressure of CO2 in the deoxygenated blood, now here, the blood, specifically the hemoglobin, has picked up CO2, and now is bringing that CO2 back to the lung capillaries, where this partial pressure will be higher than the partial pressure in the alveolar space, which means our CO2 will want to diffuse out into the alveolar space, and then it will continue to diffuse out towards that low partial pressure in the environment, in the atmosphere. We're going to have continued diffusion of CO2 during transit time, right, as we pass through the lung capillaries, until we reach equilibrium with the alveolar space. And so the oxygenated blood, we should get a reading for the partial pressure, the PCO2, of 40 millimeters of mercury in the plasma. That's on average. And then finally, what we don't have noted here is we do have some exchange of nitrogen. We do have a small amount of nitrogen gas in our plasma, in our body fluids. And here, the nitrogen gas, say PN2, would remain about 573 millimeters of mercury for the blood coming from the veins, that deoxygenated blood. And so since it should generally match to the partial pressure in the alveolar space, we're already at equilibrium. We don't get much exchange there. And the reason why we maintain something close to that 573 millimeters of mercury, and it doesn't change very much throughout circulation, is because it's inert, because our body is not using that nitrogen gas. It just stays there. I'm just going to make that note here, being that it's inert. Right. Okay, so let's break this down, because this will be useful when we look at that that carbon monoxide correlation later on. Normal values for arterial blood draws. Whoops. Normal values for arterial blood draws. We expect that if we measure the partial pressure of nitrogen in your arterial blood, it should be at 573 millimeters of mercury. It should not fluctuate very much, especially if you are haven't changed altitude, for example, or haven't gone deep sea diving. Then we have partial pressure of oxygen and partial pressure of CO2. Partial pressure of oxygen within your arterial blood will be around 95 to 97 millimeters of mercury. Keep that in mind. Notice that here we show that at first it's at 100 millimeters of mercury. And that's true. We start off with that partial pressure of oxygen as we leave the lung capillaries. But as soon as we leave the lung capillaries, then that blood is going to come across tissues that have oxygen requirements and begin to release oxygen to tissues. And then that partial pressure is going to begin to decrease within the plasma, just slightly, to 95 to 97 millimeters of mercury. And generally what that means is we no longer have 100%, 97 to 95% saturation. Maybe more typical within arterial blood. Okay. But we can see 100% saturation with the arterial blood, mainly because the oxygen that diffuses first to the tissues is that which is in the plasma before we begin to see the oxygen associated with the hemoglobin in the red blood cells begin diffusing to the tissues. If you're what are called peripheral chemoreceptors, those that are associated, say, with your aortic arch, and those that are associated with your carotid arteries, your glomerulus cells, those peripheral chemoreceptors sense a drop in partial pressure of oxygen below 60 millimeters of mercury. That drop is quickest to stimulate those receptors, which will then trigger the medulla oblongata a respiratory center, breathing center, to increase rate and depth of ventilation. That's described later on in the nervous system control over ventilation towards the end of this lecture, which I also have posted for you as a video. But we can begin to see how these numbers here, all described on this one slide, become important normal values and values to pay attention to. Then partial pressure of CO2, we've already talked about these levels in our acid-base balance lecture in terms of normal values. We expect for normal arterial blood to find a partial pressure of CO2 that ranges between 35 and 45 millimeters of mercury. And we're using 40 here on this diagram as an average. Okay. So here's a quick question for you. For those of you, maybe there's some of you who would have already done the central nervous system review of our respiration, the ventilation review here at the end of this lecture. What would be most likely to trigger a response by the medulla oblongata respiratory center? An increase in the partial pressure of CO2 to 55 millimeters of mercury, or a drop in the partial pressure of oxygen to 80 millimeters of mercury. What do you think?
CO2.
CO2. Why the CO2? Because they're both technically can be used as signals, but why the CO2?
Aren't there receptors, central receptors focused on CO2 pressure, and oxygen pressure doesn't make a difference until it's really low?
Exactly. Say that again one more time, McKenna.
Sure.
That was excellent.
We have central receptors and peripheral ones, and the central ones are focused on the pressure of CO2, and pressure of oxygen won't make a difference until it's really low.
Until it's really low, right? or if the partial pressure of CO2 is chronically high, and then also the peripheral chemoreceptors become much more important there. The levels of oxygen will then be tracked and become more important. But that was perfect. Thank you for that. Right. So that might be a question I ask, not on this exam, but on that 30% of the final exam dedicated to the rest of this respiratory material. And that covers information, like I said, from Henry's law through what we're discussing right now onto the brain mechanisms that detect and respond to changes in these partial pressures and hydrogen ion concentrations.